morning, good afternoon, and good evening. Thank you for joining us today. My name is Brent Berenson, and I'll be the moderator for our presentation. I'm director of Fluor's Office of Technology, which focuses on using science, innovative engineering technology to build a better world. Our engineers, designers, and experts, our people, are the core of our success. Today's webinar is titled Hydrogen Storage and Pipeline Transportation Design. As the world moves toward net zero energy solutions, hydrogen can supply the energy our communities and economies need to thrive and prosper. However, the use of hydrogen poses several unique design challenges due to its physical and chemical properties. With us today is David Cheng. David is a Fluor Fellow and a Technical Director in Flow Assurance and Pipeline Engineering. He has more than 30 years of experience in flow assurance, pipeline engineering, and pipeline hydraulics. He holds a PhD and Master of Science in Mechanical Engineering from the University of Notre Dame and a Master of Science and Bachelor of Science in Hydraulic Engineering from Tsinghua University. David is a registered professional engineer in Texas. He has published more than 29 peer-reviewed journal and conference papers on hydraulics, flow assurance, and particle adhesion. Currently, David serves as a chair for ASME VVUQ60 on energy systems. He is an associate editor for ASME Journal of Verification, Validation, and Uncertainty Qualification. ASME Journal of VVUQ is a Scopus indexing journal. Outside of work, David enjoys reading and collecting recipes of international cuisines. Joining David is Wendy Quach. Wendy is a flow assurance engineer based in Calgary, Alberta, Canada. She has over 10 years of experience in flow assurance and transient hydraulics. She holds a Bachelor of Science in Mechanical Engineering from the University of Alberta and is a registered professional engineer in Alberta. Outside of her work in hydraulics, Wendy's a novice baker and an avid mountain-loving yogi. Fluor has a very strong safety-driven culture, and as such, it's customary for us to start our meetings with a brief safety topic. Wendy, please unmute your line to share your safety topic with us.
Thank you, Brent. So our safety topic today, as it relates with our webinar, is on hydrogen embrittlement and an incident that occurred when a check valve shaft blew out. Hydrogen embrittlement is an important condition to consider when looking at hydrogen systems. It refers to the condition when metal becomes more brittle due to the diffusion of hydrogen into the material. And when materials become more brittle, there's a higher chance of cracking and leakage, and this can lead to equipment damage. And as we know, hydrogen is highly combustible, so if leakages occur, explosions can occur and the failures can be catastrophic. And this is exactly what happened in 1997. There was an incident of hydrogen embrittlement in a check valve that caused the shaft within the valve to blow out. The valve failure released a large vapor cloud of hydrogen and hydrocarbon gases, which subsequently ignited. And this resulted in several workers sustaining minor injuries, unfortunately, and millions of dollars worth of equipment were damaged. So if we take a look at a cross-sectional view of this check valve, you can see in this red circle here, that was the location of failure, specifically in the dowel pins. The dowel pins are made out of hardened steel, which is more prone to embrittlement. And they're also used to retain the shaft within the check valve. And so when the pins failed, the shaft blew out. And this is what caused the leakage and explosion. And it's also worthwhile to note that check valves and butterfly valves are particularly susceptible to this condition because of their geometry and because they typically undergo higher cyclic loads from having to open and close more frequently. And so from this incident, there were a few lessons learned. For one, it's important to inspect hydrogen facilities to determine if there are valves that are at risk of hydrogen embrittlement. And if so, consider replacing or modifying the valves using a blowout-resistant design. And if the valves are being modified, it's also important to consult the valve manufacturer to ensure that any potential modifications are safe. This incident was obtained from a document issued by the U.S. Department of Energy. And if you would like more information, the website is shown here. And with that, I will conclude the safety topic and pass the mic back to David.
Morning. We are going to talk about the various energy sources in the world the potentials and challenges of using hydrogen as a clean energy carrier, and the design of infrastructure required in massive hydrogen storage and pipeline transportation. On this slide, I wanted to show you the energy sources currently available to us in the world. We basically are using renewable and non-renewable energies. We are very familiar with non-renewables such as natural gas, oil, coal, and nuclear. We also have renewables such as biofuel, solar, wind, hydropower, geothermal, and tidal energy. Pretty much these are all the renewable energies that we know so far. Two of the biggest challenges we are facing globally today are the climate change and the continuous increase of energy demand. Based on the U.S. Energy Information Administration data, U.S. consumes total 93 quadrillion BTU of energy in 2020, which is 7% lower than that of 2019 due to the impact of the COVID-19 pandemic. However, the projection of the U.S. and world energy consumption continue to grow dramatically in a foreseeable future. On the other hand, among all the total energy consumed in the US in 2020, about 79% was still from fossil fuel and 34% was from natural gas. The consumption of fossil fuels was the major source of carbon emission and global warming. Emissions must peak by 2025 to prevent disastrous climate change effects, according to the new UN climate report. The increasing energy demand and global warming control are now in conflict. It is therefore necessary to phase down the use of fossil fuel and increase the percentage of renewable energy consumptions. Given this global consensus, also agreed by the US, we must think about how to make the best use of existing massive fossil fuel system to transition to a clean energy system. The increasing energy demand cannot be met through increasing the renewable energy production without resolving its major limitations. The major obstacle of using renewable energy is not only its high cost, but also the misalignment between its production and the consumer needs. Hydrogen for a long time has been looked at as a clean energy carrier that can help to improve the alignment between renewable energy production and energy needs. Hydrogen can be produced from renewable energy as green hydrogen and from non-renewable sources with carbon capture and sequestration as blue hydrogen. Hydrogen is also the byproduct of many chemical plants. The production, gathering, storage, and transportation of hydrogen will be an important part of the clean energy system to help to control global warming. Need to emphasize that CO2 capture and sequestration. It's possible to continue to make the best use of fossil fuels and infrastructures to make it clean by removing the CO2 content. Carbon capture and sequestration is part of the blue hydrogen production using non-renewable energy sources. That procedure is related to the hydrogen economy too. These charts compare the energy value of hydrogen with other common fuels. Hydrogen has very high energy content by mass, nearly 3 times more than conventional fuels, however very low energy content by volume as a very light gas. Fuel cell power generation using hydrogen is very clean. It only produces water. However, the combustion of hydrogen in air as a fuel can lead to thermal formation of nitrogen oxides, another greenhouse gas. When released directly, hydrogen itself can interact with other gases and vapors in air to produce powerful warming effects. A new UN government study determined that hydrogen's global warming potential is about twice as bad as previously understood. The table on the right shows the estimated hydrogen emission. However, thanks to the very high energy mass contents of hydrogen, even assuming the worst leakage scenario, it is still an enormous improvement in global warming by using hydrogen. The benefits outweighs the disadvantages in using hydrogen. The researchers did clearly demonstrate somehow the importance of controlling hydrogen leakage within a hydrogen economy. Because of the promising benefits, the U.S. Department of Energy produced a national version of America's transition to hydrogen economy. This chart shows a roadmap. Our focus today is about the storage and delivery of hydrogen. As you can see in the middle, the roadmap related to the storage and transportation of hydrogen in the future is an integrated central distributed network that are targeted in the year 2040. Based on the U.S. Department of Energy's vision, gaseous hydrogen pipelines will be an important part of the whole hydrogen infrastructure, as shown on this chart. The whole life cycle streamline of hydrogen production, storage, transportation, and distribution is very similar to the massive oil and gas infrastructure systems that the U.S. currently has. In the future, hydrogen will be produced in central production facilities. The hydrogen will be collected through the gathering system into hubs. From there, hydrogen will be compressed as gas and transported in major trunk lines, interstate or intrastate pipelines, and stored in massive storage facilities. Hydrogen will be delivered to end users from storage facilities through distribution pipeline networks. In recent years, there's also motivation to use ammonia as a carrier and a chemical storage media for hydrogen. Ammonia is liquid in normal condition. The molecule is bigger with much lower leakage potential in metal pipes. It has lower volume and higher mass of hydrogen contents if transported in pipeline. However, there are higher nitrogen oxide emission risks associated with the production and application of ammonia comparing to pure hydrogen. Ammonia is ideally suited to be made from green sources and can be efficiently shipped in massive volume globally through the marine system. Once imported, ammonia can be decomposed back to hydrogen into the onshore integrated hydrogen network. However, ammonia is highly corrosive, requiring to be contained and shipped in very dry conditions. Ammonia is not an ideal medium for long-distance pipeline transport. The maintenance cost is very high comparing to other pipelines. Magellan Midstream decommissioned its 1,100-mile Texas to Upper Midwest ammonia pipeline in 2019 due to its unforeseeable high operation and maintenance cost. Today's discussion focuses on the onshore pipeline transport systems, and hydrous ammonia pipeline will not be our focus, but we understand the potential role and the strong interests of ammonia in the global energy system. This slide shows the current technologies in the storage of hydrogen. We see from the chart on the left that there are three types of storage. The critical temperature of hydrogen is 13 K, and the critical pressure is 33 bar. So hydrogen can be stored at temperature below the critical temperature as liquefied hydrogen. The second option is hydrogen can also be stored and transported in pipeline or vessels with very low density at normal temperature as gas or supercritical fluid. Third option is hydrogen can be stored at supercritical condition in underground geological storage. The last option shown on the chart on the right, the chemical hydrogen storage. For example, hydrogen hydrogenated or dehydrogenated in organic or metal material. To build an integrated central distribution network at the national level, the utilization of pipelines and underground storage facilities are necessary. Pipeline enables massive transportation of hydrogen as gas or supercritical flow. Pipeline is safe and very economical. Cost of pipeline transportation can be reduced through the optimization in design and operation. We will demonstrate the J-curve analysis in later slides to demonstrate the minimization of total cost per throughput of transport in pipeline design. The minimization of the transportation cost helps to lower the overall cost of using hydrogen as a clean fuel. Based on the framework of the integrated central distributed hydrogen network, we listed the conditions for hydrogen transport and storage most likely in the future. The transmission pipeline will operate at around 55 to 85 bars, which is ASME 600-pound class system. Geological storage will be at 100 to 670 bar, which is above ASME 2500 pound class rating, for components near the bottom of the underground storage. The surface area will be lower class rating. We will also need large flow rate centrifugal compressors capable of producing 85 bar discharge pressure for transmission pipelines, and reciprocating compressors capable of producing 330 bar discharge pressure for underground storage injection. The terminals and the distribution networks of hydrogen will be at 52 to 83 bars. It's also ASME 600 pound rating. Geological storage provides a massive capacity for the future. Those storage include underground salt dome caverns, depleted gas reservoirs, aquifer, hard rock cavern. The later slides will show the latest reported data about the existing underground gas storage facilities in the U.S. The U.S. currently has total 453 underground gas storage sites. Salt dome caverns are a promising hydrogen storage solution. They can provide a huge capacity in the 100 gigawatt-hour range. Generally, rock salt has a very low hydrogen permeability, which ensures minimal loss of hydrogen or contamination with the geological surroundings. Potentially, salt dome caverns can store hydrogen at pressure more than 100 bar, with fast storing and releasing rates. Examples of existing hydrogen salt dome cavern storage are shown here in the table. There are currently three types of concepts on long-distance transmission pipelines for hydrogen. The first one is blending of hydrogen in existing natural gas pipeline network. Second is construction of pipelines for pure gas hydrogen. and the third one is liquid ammonia pipeline. We mentioned the high maintenance cost of ammonia pipelines, so the anhydrous ammonia pipeline is not discussed today. Pipeline transmission of hydrogen is not something new. It dates to the late 1930s. It has a very good safety record. Normally, hydrogen pipelines operate in under 69 bar G. The U.S. currently has 2,538 kilometers of pure hydrogen transmission pipelines in operation. In Europe, it's about 1,700 kilometers. The current long-distance hydrogen pipelines in operation in the U.S. are mostly along the Gulf Coast. They transport hydrogen to well-established long-term chemical and manufacturing users. Germany has about 209 kilometers of pipeline carrying 220 tons per day of hydrogen in a 10-inch pipeline with very low operating pressure of 20 bar. The U.S. natural gas pipeline system has evolved from local networks serving municipality in the mid-1800s to a vast network of interconnected pipeline systems with 3.9 million kilometers of pipe, more than 400 underground storage facilities, and more than 1,400 compressor stations. Natural gas accounted for 34% of U.S. energy consumption in the year 2020. Moreover, recent increase in U.S. gas production rates suggests that existing natural gas system will continue to provide relatively clean energy for some time, especially with increased adoption of energy efficiency measures. Given these characteristics, hydrogen blending could become a widespread, long-term, and integral practice to supplement a critical U.S. energy infrastructure. Actually, the U.S. Department of Energy has been working on this for years through the HyBlend project. INGA, the Interstate Natural Gas Association of America, also released their RFP for developing a guideline in blending hydrogen in existing natural gas systems. Europe could devote, based on the news, 40,000 kilometers of natural gas pipelines to hydrogen by 2040. The blending of hydrogen in existing natural gas system provides an economic opportunity in gradually transition to the hydrogen economy. With modification and changes, the existing gas system can also be upgraded to handle pure hydrogen. The upgrade of the existing system can be the most cost-effective way with minimum waste and environmental impact comparing to new construction of pipelines and storage for pure hydrogen. It has been proven by pilot studies that the system requires little or no change for hydrogen concentration less or equal to 20%. The cons are it requires downstream hydrogen extraction and recovery at regulation stations for hydrogen end users. The economic trade-off evaluations are necessary to obtain a cost benefit. Blending of hydrogen in the system also has impact to end user equipment and operation efficiency. Whether the safety and high leakage potential of hydrogen have major impacts to end users also need to be understood. Long-term durability and integrity management need to be studied and procedures need to be developed. Existing natural gas system needs to be upgraded to be able to transport pure hydrogen or blend with hydrogen higher than 20%. There are technical challenges to that. This slide shows that the concentration of hydrogen has significant impact to pipeline design and capacity. Same-size pipeline transports higher volume of pure hydrogen with lower net heating values. To transport the same heat content, the cost of pipeline is 3 times more expensive. However, the natural gas energy contents are associated with CO2. The expense of hydrogen blending in natural gas pipeline will also include the carbon capture and sequestration and hydrogen recovery. In general, a pure hydrogen system will be not only clean, but also economical. The next major challenge is material selection. There are steel pipes and non-metallic pipes available for hydrogen application. The Pipeline and Hazardous Material Safety Administration data shows up to 2021, the U.S. has total 2,538 kilometers of hydrogen transmission pipelines, comparing to total 485,000 kilometers of all gas transmission pipelines. The data shows that the transmission hydrogen pipelines in operation are predominantly carbon steel pipes. All steel pipes in hydrogen transmission are coated. Environmental hydrogen embrittlement is an issue in hydrogen services. Metal working in a hydrogen environment over a long time will cause the deterioration of material. There is no hydrogen, however, embrittlement at low pressure less than 70 bar. This is good news. Hydrogen transmission pipeline is generally operated at pressure from 20 to 70 bars. The expected service life can reach 15 to 30 years. ASME B31.12 was developed in 2014, particularly for hydrogen pipeline. It recommends the use of low-grade level X42, X52 seamless steel pipes. B31.12 also suggests a series of methods for preventing hydrogen embrittlement during low-temperature performance. Use of non-metallic material was never recorded in the gathering, transmission, and distribution of hydrogen in operation according to the FAMSA annual data. Some researchers show that reinforced thermoplastic pipes are ready to be used for hydrogen up to 42 bar, and HDPE pipes are hydrogen ready up to 15 bar. However, the design pressure of plastic pipes needs to be increased to at least 70 bar for hydrogen transmission, and long-distance testing is quite necessary. The material required for underground geological storage is much more a challenge. Underground storage operates in higher pressure range, which can cause hydrogen embrittlement. There is still research ongoing. We need to gather all the information and hopefully develop a guideline for material selection in this area. The injection and withdrawal of pure hydrogen or gas with hydrogen blending dramatically influence the thermodynamics, mixture composition, and the contamination and containment in the storage inventory. The salt dome cavern thermodynamics need to be studied to examine the potential change of temperature, pressure, and thermal stability in the cavern. Rock salt has a very low hydrogen permeability, which ensures minimal loss of hydrogen or contamination with the geological surroundings. Gas withdrawal from salt dome cavern requires dehydration in early operation years. The dehydration requires quickly decrease after a few years of operation. The gas from the cavern becomes dry. Generally, salt contamination from the cavern storage is very low. However, some researchers show the concern when very high quality of hydrogen is required. In that case, gas or hydrogen withdrawal from salt dome caverns need desalination and dehydration. The current surface dehydration and filtering equipment used for natural gas need to be evaluated on treating very pure hydrogen. The massive withdrawal of hydrogen blending from storage into the transmission pipeline systems will also impact the operation of the entire transmission pipeline systems because they are interconnected as a network. With changing of hydrogen concentration and how the operation need to be adapted, need to be studied. Gaps and risks need to be identified. Another major technical challenge is the compressor selection. We know that hydrogen volume is 3 times that of natural gas at the same pressure. Hydrogen is very difficult to compress. It has a very small molecule which has high potence of leakage through containment. The compression of hydrogen requires much more power, higher tightness, and special seals to reach the pressure required for high volume transmission. We know from compressor manufacturers that multi-stage reciprocating compressors are ready for producing discharge pressure up to 69 bar for hydrogen. This is considered the most state-of-the-art equipment for compressing hydrogen. The maintenance cost of varying parts create a technical challenge in pure hydrogen service. A centrifugal compressor capable of providing large volumetric flow rates and discharge pressure more than 83 bar for transmission pipelines is yet to be developed. Another issue is the contamination of hydrogen through compression. The DOE and INGA are supporting the compressor design studies on hydrogen pipeline and underground cavern injection requirements. Hopefully, an oil-free compressors that have a working pressure ranging up to 80 to 100 bar can be produced in the near future. Ideally, the compressor will be efficient, will not contaminate the hydrogen, will be also reliable and durable. There are other challenges, for example, in operation and integrity maintenance. Validated safety management measures for pure hydrogen pipeline. DOE, INGA, and the PRCI are leading the development of industry standards in this area. Based on the information we've just introduced, we can talk about the pipeline design and methodology for hydrogen. We think the most important thing is to have in-depth knowledge of both existing natural gas system and hydrogen pipeline systems. The design will focus on material and equipment availability, cost, and safety. It also needs to consider uncertainty, including the purity of hydrogen in the system. Need to mention that artificial intelligence may provide the cost-effective way in hydrogen pipeline routing. For hydrogen pipeline, dispersion and rupture impacts will be different. This can be considered efficiently using artificial intelligence tools. The design also needs to be based on solid construction data. Advanced tools in figuring out the cost basis on construction based on construction experience are quite necessary. The pipeline also needed to be economically optimized to be able to demonstrate the cost saving and carbon footprint reduction. It's necessary to compare the general cost of a pure hydrogen system versus a natural gas system with carbon capture and sequestration. Fluor's technical capability are very well suited in hydrogen pipeline and storage design. Our capabilities, first of all, are guided with in-depth knowledge and history data. We have the understanding of the thermodynamics and flow assurance principles necessary for design. We have a very good history of understanding the client's operational and capacity needs. Our philosophy enables us to produce flexibility with maximized return of investment and minimized transportation costs. We have in-depth understanding and consideration on the safety of supercritical and gaseous hydrogen pipeline design. We mention particularly supercritical flow because we call hydrogen pipeline as a gas pipeline, but based on the operating conditions of transmission systems, the hydrogen is actually in most operating conditions supercritical fluid. This chart shows the typical pipeline system design optimization procedure that we follow. We start with initial design based on history data. We start with a design that falls in the normal operating range of existing systems. We then work together with client in determining the required flow capacity and the stages of operation and construction, and the flexibility in the future for expansion or downsizing. Different pipeline routes are then selected for economical and technical comparison. For each of the candidates of pipeline routes, there is the J-curve analysis for maximization of cost saving in pipeline design. Throughout the J-curve analysis, the optimized design is developed for every candidate pipeline route. The cost and savings for each pipeline route are then screened based on the J-curve analysis results. This procedure produces the minimum total transportation cost per throughput of the pipeline. The J-curve analysis is a widely used economical optimization method accepted in the gas industry. The J-curve analysis considers the ballpark cost of the pipeline through scaling with capital expenditure, operation expenditure, and financial cost basis. The J-curve analysis starts with building a scalable basis for ballpark cost estimate. Based on the pipeline constructability analysis, a cost base for capex per unit size and length of pipeline, unit power installed in compressor stations are developed. The OPEX include the cost basis for power or fuel and operation maintenance cost as a percentage to annualize the capital cost. Next step is to define the operating range, basically the throughput over the life cycle of the system. Then a pool of candidates of pipeline sizes based on history range of pipeline flow capacity are defined. The hydraulics model is then used to calculate the compression power and the power loss, pressure loss of the system to provide the data for the calculation of capex and OPEX of the pipeline. The transportation cost per unit put is calculated as the capital cost, operation cost plus financial cost per unit throughput of hydrogen. The transportation cost is calculated for a range of throughputs. Once the transportation cost is produced, the J-curve can be generated for various pipe sizes, compressor station spacing, and pipeline routes. The optimized diameter and the corresponding compressor station spacing will then be identified to the minimum transportation cost of the project life cycle. So in summary, the J-curve analysis result leads to the design of the maximized return of investment. This shows one example on initial selection of pipeline size. The compressor discharge pressure in this case is 70 bar. A compression ratio of 1.5 to 3.0 is suitable for hydrogen pipeline. Compressor station spacing is determined by the pressure available at the downstream station section for the suitable size of the pipeline. This slide shows an example of the optimized system through a J-curve analysis. The transportation cost of different line sizes and the compressor station spacing were calculated as shown in the charts. In this particular case, the 48-inch pipeline with 300 kilometer compressor station spacing produces the lowest transportation cost per kilogram of hydrogen. There are two aspects in this example. One is the transportation of hydrogen will only make economic sense with larger size pipelines that are capable of delivering thousands of tons of hydrogen per day. The second thing is decreasing the pipe length by adding more compressor station help to increase pipeline flow capacity for smaller pipes. The extra capital and operation cost of compression is worth the investment to increase the overall capacity and in return lower the cost of hydrogen transportation in smaller size pipes. However, with the use of larger size pipe, more compressor stations do not add any benefit in terms of reducing the levelized cost or transportation cost of hydrogen. In summary, today we talked about the necessity of phasing down of fossil fuel consumptions to peak the carbon emission and prevent disastrous climate change effects. We talked about the potentials and challenges of using hydrogen as a clean energy carrier. We also introduced the massive natural gas infrastructure in the US and potentially blend hydrogen into the gas system and upgrade the whole system for the hydrogen economy. Finally, we talk about the working conditions and optimize the design of the hydrogen storage and pipeline systems. That concludes my presentation for today, so I will turn it back to Brent for question and answers. Thank you.
Thank you, David and Wendy. Let's take a moment to address the questions that we've received from the audience. Again, just a reminder to please make use of the Q&A tab to ask any questions, which should be addressed to all panelists. The first question, there is a potential for reaction of hydrogen when stored underground to form hydrogen sulfide and other chemicals. What process would be proposed to ensure the hydrogen sent to users is free from these contaminants?
Yeah, so currently for natural gas underground storage on the surface, we have dehydration filtering units. So in the future, it's inevitably that we have to add the sulfur removal system in the process. And what is the removing efficiency of sulfur from hydrogen that needs to be studied, and it is a technical challenge.
Thank you, David. The next question, what is your biggest concern with implementing higher levels of hydrogen in existing pipelines?
The biggest concern is the pipelines in the US are interconnected with lots of trading opportunities. So it's very difficult to control the concentration level in the system. So when we evaluate the pipeline conditions for higher hydrogen concentration, not only we should evaluate some local area, we also need to evaluate all the tie-ins, so which is a big task. And the challenges are associated with the topic we mentioned today. So we need to check the efficiency of the compressor, whether they will be okay. Because to transport the same heat content, it required much more flow rate and the compression power. And the existing pipeline already have a design pressure that you can never exceed. So and also the integrity of the pipeline. Because hydrogen is more risk for leakage. So we need to check all the valves, seals on that, and also make sure there's no minor leakage in the system. And also check whether higher concentration is okay for hydrogen brittlement. Even though we mentioned under 70 bar, the brittlement should be pretty minimum, but we still need to, because we don't know existing pipeline what type of material they have. So we need to evaluate that. So, and also to come up with an operation and maintenance procedure, which is cost effective. That's also the concern. So those are the area in my mind we need to pay attention to.
Thank you, David. As a follow-up to the previous question about the potential for reaction of hydrogen when stored underground, can hydrogen stored underground meet the 99% purity required to power hydrogen fuel cells?
Based on the experience, yes, because we do have hydrogen storage in salt dome caverns in operation currently. Not only the U.S., UK, and some other countries too. So the answer is yes, but the procedure will not be once for all. The initial period in operation, because of the leaching process left humidity in the salt dome, then you have to go through several injection withdrawal cycles for the humidity to decrease to a allowable range. So hydrogen in the salt dome may or may not achieve 99%, but with dehydration and removal of contamination, it will, reach 99% again.
Okay, and then can the sulfur recovered from the hydrogen source be further processed for fertilizers, etc., to increase the economic value of using hydrogen?
It depends on the amount. That amount may not be significantly enough for you to be able to use it as a fertilizer.
Okay, thank you. What is the experience so far on composite pipelines for hydrogen service?
The composite, based on the record, there's no such pipe in operation. That's what I saw in the FAMSA database, because you have to report it to FAMSA if you have a transmission, gathering, or distribution pipes, and you have to report the service. And I don't see any those kind of pipes are used in recorded in operation.
Thank you. How do we determine the location of underground storage systems for hydrogen? Is it near the generation unit or near the consumer?
That's one disadvantage of salt dome caverns. So because they are located based on the geological availability, not consumer or production. So they serve as a massive storage. not small scale storage. So to inject or withdraw from a salt dome, you need to be hooked into the national gas transmission system. That's the purpose why we wanted to blend first hydrogen into the pipeline to be able to inject into those salt dome caverns. But they did serve as a very big cushion to be able to use as a energy peak and valley adjustment.
Okay, thanks. Is the electrical or hazardous classification higher for hydrogen than natural gas? Does this impact selection of electrical and instrumentation?
The impact radius will be different. It's lighter than natural gas, therefore, on the horizontal direction, it may not be increasing, but the vertically, it will be different because it's easier to disperse into air.
That makes sense. Next question relates to the auto industry. What is the potential future for the auto industry, hydrogen versus lithium-ion battery, for example? If in your opinion, which one will play a bigger role economically and technologically in the future to replace gasoline in autos?
So I see both of them will play big roles. And hydrogen right now, hydrogen-driven cars are, not massively available. The reason is, that there's no infrastructure built yet, and the electricity infrastructure is getting better and better. So, in my opinion, it's an economic evaluation issue. So, how to distribute the energy through hydrogen or electricity? Need to have some national level consideration in the planning. To the battery has certain limits. Uh, the duration of the battery, the capacity of the battery, and the material availability for making the battery is all limited. That's the strength of hydrogen. So, and the hydrogen is very clean if you can reduce the emission to a minimum level. So it only generates water. So hydrogen can be more powerful. You don't need so many electric charging stations, and the charging time can be tremendously low using hydrogen. This too, I think I can see in the foreseeable future that hydrogen cars and vehicles will increase. And currently we don't have it is because of the investment on infrastructure. But we are seeing that this area is picking up. People are doing all kinds of studies and engineering design, and hopefully some major facilities will be built. But based on the news you see in Houston, in Dallas, and everywhere, there are new facilities for hydrogen in the building.
Great, thank you. Has Fluor designed underground storage facilities for hydrogen in the past?
We don't, but Fluor is the contractor operating all the SPR, Strategic Petroleum Reserve underground salt dome cavern systems. So we are the operator is already 10 years. So we have rich experience in the operation of salt dome caverns, and we also have experience building the CO2 sequestration in salt dome caverns and the natural gas storage. And those, as I mentioned, are important part in the knowledge basis. And the hydrogen part, and we understand the thermodynamics, which is an important part in the simulation of the salt dome system. we understand the material. We have the metallurgy people who has first-hand experience building the hydrogen system on the surface that can also be used, those kind of knowledge in the underground area. So, but of course, we need to work together with geologists in, and the leaching process design, those kind of things.
All right, thank you. Are there any differences between Europe and North America in terms of hydrogen transportation and or storage?
There's no major difference. Europe also has pipeline and salt dome cavern storage and some other type of storage. So they also have massive networks of natural gas system, and they have a similar plan, which is to blend hydrogen into the gas system first, and then also on the same time build the pure hydrogen network system. And hopefully in the future they can merge. And as far as operation, currently I showed in Europe, it seems the operating pressure is pretty low. So they need to increase the pure hydrogen operating pressure in the future, which is also what we are doing. We are looking at a guideline, generating a standard to be able to increase the operating pressure.
All right, thank you. And it looks like that's all the time we have for questions today. Thank you again, David, for this informative webinar and the time you've spent today and in preparation. And thank you to our audience for attending today. It's been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com, following our social media channels using hashtag Innovation Builders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. From all of us on the Innovation Builders team, have a safe day.